Welcome to the final exam review of OCHEM 242 lab. Your exam will be on next Wednesday, that is 12th of August, and it will start at the usual class time, that would be 11:20 a.m. So make sure you are available for that time. If for some reason you cannot start the exam at 11:20 a.m., please make sure that you email me beforehand so I could make arrangements for that. And the exam should be about 1 hour. It will be all multiple choice questions, about 20 to 25 questions. And this is very important. Once you answer a question and move on to the next question, your previous answer will be locked, so you cannot go back and change it. Let's quickly look at the focus areas for studying. Look over the concepts for each lab, the purpose of specific reagents used in an experiment. For example, we used 3 mol HCl in the Grignard reaction lab. The purpose of it was to specifically protonate the final product into an alcohol and get rid of any leftover magnesium. So those kind of reagents that we used in some of the experiments, make sure to note down the purpose. Then the techniques involved in isolation of the product, such as extraction, and techniques for purification that we mostly use recrystallization technique. Then calculation of theoretical yield and percent yield. Make sure you pay attention to the molar ratios. Then chemical reactions. The type of reaction mechanism, is it nucleophilic substitution type 1 or 2? Make sure you know what type of chemical reaction it is. Then you should be able to predict the products. So if you were given two reagents for ether synthesis, or you were given a molecule that will be reduced, it's a ketone reduction experiment, or you were given a Grignard reagent with another molecule for Fischer esterification, Michael addition, aldol condensation. For all of these, practice predicting the product if you were given the starting material. Or in some cases, you could be given the final product and asked to predict what were the starting materials. Deciphering IR and HNMR spectrums, and predict repeating the units for condensation polymers when we use bifunctional monomers, or else if you are given the repeating unit and asked to predict what were the bifunctional monomers that condensed to give this repeating unit, then you should be able to predict those monomers. So you can use this as a guide when you're studying. Let's quickly remind ourselves of the IR spectroscopy technique. So when we looked at a spectrum, we had 3 different properties that allow us to distinguish different kinds of bonds. So we had wave number, intensity of peak, shape of peak, and for wave number, we learned that stronger bonds would have a higher wave number. So stronger bonds are triple bonds are stronger than double bonds are stronger than single bonds. Those kind of bonds would appear towards the higher end of the x-axis. And the intensity of the peak was depending on the dipole moment, that is, how much of a dipole exists. Like for example, in the OH bond, the electrons are mostly shifted around oxygen. So there is a permanent dipole, and bonds like this bond would absorb light very intensely, so we would see less amount transmitted because y-axis gives the transmittance, so we would have a more intense peak. And the shape of the molecule depended on intermolecular interactions such as hydrogen bonding, which is why we see a broad peak for the OH group, for example. And if it's a carboxylic, if it's a OH from a carboxylic acid group, this peak would be even more broader because it can participate in even more hydrogen bonding. So make sure you practice predicting or identifying these peaks. So if you are asked a question like this one, if you are given a spectrum and asked to predict which molecule is represented by this spectrum, you should be able to identify the correct molecule. So if we quickly look at this IR spectrum, this peak over here is for CsP3H stretch. Since it's very intense, it indicates that this molecule probably has many CH2, CH3 groups. Then over here, we have the distinct peak for the carbonyl bond. And over here, another strong peak where we usually see a CO bond. And other than that, we don't have any other peaks showing us the presence of any major functional groups. So when we look at the answers, the C and D answers both have aromatic rings on them, but when we look at the IR spectrum, we have no evidence for the presence of the aromatic ring. So you are able to eliminate these two answers. Then we can look at these two. This one has the OH group. If there was an OH, we should have seen a broad peak around this region from 3200 to like 3600, but there is no peak there. And our last choice is this ester. We have a carbonyl, a peak for the carbonyl bond, and we have a very strong peak for the CO bond. So that would indicate that there is a CO bond present. And we have these additional peaks as well, indicating CH3 and CH2 bending. So all of that suggests this could be an ester, and it has many CH2 and CH3 groups as well. So you should be able to predict that this is your answer. Let's quickly remind ourselves about the proton NMR spectroscopy. So we discussed a few concepts related to that. First, the chemical shift is the number that you would see a peak for specific protons appear on this axis. So if a certain proton is more exposed, that is to say, it has less electrons flowing around it, as it happens when it's attached to a highly electronegative atom, then it's more exposed to the external magnetic field. So it will absorb at a higher frequencies, therefore it should have a higher chemical shift. Versus a proton that would just be like in a CH3 group next to more R groups that do not cause a significant shift of the electron clouds around the protons, then those kind of protons are more shielded from feeling the strength of the external magnetic field, so they should have a lower chemical shift. Then the chemical equivalency is, that means the protons that share the same chemical environment. So you should be able to identify how many chemical equivalent protons are available in a given structure, because that will decide how many peaks you would get on your NMR spectrum. It means protons that are in the same chemical environment, they would all appear as one peak. Then the integration of peaks gives us the number of protons represented by each peak. Sometimes the number is directly linked to the number of the molecular formula you're given, but sometimes you will be given the ratio. Then you will have to see how many protons based on the molecular formula. You have the total number of protons, and based on the ratio you can decide how many numbers of protons are represented by each peak. Then the coupling rule, that is the n+1 rule, helps us determine how many neighbors are next to a group of chemically equivalent protons. So here's a quick cheat sheet to remember the different types of protons. So even though you don't remember the exact numbers, that's totally fine. All you have to remember is a proton from a carboxylic group would have a very high chemical shift because it's next to a very electronegative functional group, versus protons that are in like a CH3 group or a regular alkene or like that, they would have a lower chemical shift. And you should specifically remember the protons on an aromatic ring would appear in the 6 to 8 ppm range. So there will be questions where HNMR spectrum is provided and you are asked to pick the correct molecular structure from the given molecule structures. So if we quickly look at this, here is a peak to a doublet. This is a doublet representing 6 hydrogens. And that would automatically mean there are 2 CH3 groups that are chemically equivalent, and their neighbor has only 1 hydrogen. And over here we have a multiplet that represents just 1 hydrogen, so it's probably a CH group, and it has a whole bunch of protons on their immediate carbon neighbors. Then over here we have 2 hydrogens represented here, which is also a doublet. So it would indicate this must be a CH2 group, and its neighbor has only 1 hydrogen. Over here we have 1 hydrogen represented by this singlet. So if it's not divided, not split into any peaks, this 1 hydrogen would usually indicate it must be an OH group, especially if it's around 3.5 to 4 ppm. So we have an OH, we should have a CH2 group which has 1 immediate carbon neighbor who has only 1 hydrogen on it because of the number of splits. And now we have accounted for this group, and this one. So the last 2 CH3 groups must be here. And let's check if that makes sense. So they are both attached to this carbon, and that carbon has one hydrogen, and on this side a CH2OH group, so they're chemically equivalent. And then it has this immediate carbon neighbor who has only one hydrogen. That would cause that peak to split to two, so it makes sense. And let's double check on this hydrogen. It's split to 1, 2, 3, 4, 5, 6, 7, 7 peaks. That means their neighbor must have 6. So these two are the immediate carbon neighbors, as well as over here. So we have 6, actually 8 neighbors. So this probably has more splits, but we're not able to see it because the resolution is not clear enough. So let's scratch that off. So n equals many neighbors. So that makes sense, and that's how once you choose a structure, go back and double check and match with the spectrum to see if it makes sense. Our third lab was Williamson ether synthesis, and this is a pretty straightforward lab where we use a reaction between an alkoxide or a phenoxide with alkyl sulfonate or alkyl halide in order to prepare a respective ether. So practice predicting the resulting ether if you're given an alkoxide or a phenoxide and an alkyl halide or alkyl sulfonate. In our lab, we used 4-ethylphenol and we converted it to a phenoxide by reacting it with sodium hydroxide. And then it was reacted with ethylptoluene sulfonate to prepare this ether. And remember, we used this reagent called TBAB, which was a phase transfer catalyst. So this is a specific reagent that you should remember what its purpose was. And the whole point of using TBAB was we would have the 4-ethylphenoxide, we would have 4-ethylphenoxide in the aqueous layer and this one in the organic layer. And to bring them into contact, we use TBAB, which would be on the interface because it had both polar groups as well as non-polar groups. So it will attract these reagents to the interface and then they can react. So that was its purpose. And in the final mixture, aqueous, organic, the ether would be in the organic phase and this side product, you can see it's an ionic molecule, so it would be in the aqueous phase. But if we had any leftover 4-ethylphenol from the beginning, that would also be present in it would be present in the organic phase. And we used extraction to isolate the product, and during extraction we washed the organic layer with 5% NaOH to remove any leftover 4-ethylphenol from the organic phase. So let's say if you're given IR spectrum and told to look at it and see, okay, this person was trying to obtain an ether. Was he successful or not? You look at the IR spectrum, and if you see a peak around where you expect a peak for OH, that would indicate you have 4-ethylphenol that's left over. Then how can you remove it? You remove it by reacting it with 5% NaOH. Then it will be converted to this phenoxide, which is ionic, so it should move from organic to aqueous phase. Then we did ketone reduction, where we reduced a ketone into its respective alcohol. We used sodium borohydride in ethanol, and we used that because it's much safer, and we only needed to reduce a ketone. So NaBH4 is sufficiently strong to reduce a ketone to the respective alcohol. However, you should remember why lithium aluminum hydride, which was the other reducing agent that we discussed, why it's a stronger reducing agent compared to sodium borohydride. And we discussed 3 reasons. One was that aluminium is less electronegative than boron. So aluminum has a much weaker bond with hydrogen, so the hydrogen can easily leave compared to hydrogen that is attached to the boron. That was one reason. Then lithium ion was better at stabilizing the carbonyl oxygen than sodium. And the other reason didn't really have to do with the reducing agent. It was really the structure of the carbonyl compounds. So if there is a carboxylic acid or ester or an amide, those kind of structures have more resonance groups, therefore they are more stable. The more resonance structures, the compound is more stable. So you would need a stronger reducing agent in order to reduce those kind of carbonyl groups compared to ketones and aldehydes, which have lesser amount of resonance structures, so they're more susceptible to be easily reduced. And in this lab, we again used extraction as the technique for isolation. And we used the specific reagent 3 molar HCl, and the reason was to get rid of any excess sodium borohydride. So that reacted with HCl and water to give sodium chloride, boric acid, and hydrogen gas. Our next lab was the Grignard reaction. We learned about preparing of a Grignard reagent. We react an alkyl halide or aromatic halide with magnesium in the presence of anhydrous solvent like diethyl ether in order to obtain an organomagnesium halide, which are the Grignard reagents. So if you're given the reagents and asked to predict the structure of the Grignard reagent, you should be able to do that. And if you're given the Grignard reagent and asked to predict what were the starting materials, you should be able to predict that. And remember, we did not want any water to be present in the glassware or in the reaction mixture, because Grignard reagents can act like strong bases and can react with water in an acid-base reaction, and degrade this Grignard reagent. So we don't want any water in the reaction mixture. And specifically, the experiment we did was to prepare phenyl magnesium bromide as the Grignard reagent and then use that in a reaction with methyl benzoate and ester to produce this triphenylmethanol. Just like here, you have to practice if you're given reagents and asked to predict the final product, you should be able to do that. As well as if you're given the final product, you should be able to predict what was the Grignard reagent and the other molecule reacting with it. So again, we used extraction as the isolation technique, and we purified the product by recrystallization, and we used 3 molar HCl in this lab as well. And the main reasons were to protonate the triphenyl methoxide into triphenyl methanol and to decompose any leftover magnesium. And as an indirect purpose was to give some aqueous phase to the reaction mixture, so we would be able to do extraction. Our next lab was Fischer esterification, where we prepared this isopentoyl acetate through the Fischer esterification method. This is when we react a carboxylic molecule with an alcohol in the presence of a strong acid catalyst like sulfuric acid. Just like in the previous experiments, if you were given a carboxylic acid molecule and an alcohol, you should be able to predict the respective ester and vice versa. So remember that we discussed if the alcohol is a tertiary alcohol, it would not participate in Fischer esterification, but if it's still in the presence of sulfuric acid, it will undergo a dehydration reaction and produce the respective alkene. And we discussed 2 ways to improve the yield of the ester. One way was to reduce water or remove the water when it forms. That means the reaction has to shift towards the forward direction to make sure that change is rectified based on the Le Chatelier principle. The other way was to add a large amount of one of the reagents to make sure we get the highest possible yield. So that's the answer to this question. And again, we used extraction as the isolation technique. And we washed the organic layer with sodium bicarbonate during the extraction. Since we added excess reagent, in our case we added excess amount of acetic acid, so it's going to be mixed in the final mixture with isopentoyl acetate, and we needed a way to get rid of that, and that was by reacting it with sodium bicarbonate, which is a base, so we convert the carboxylic acid into its sodium salt. So now it's an ionic compound, therefore it will dissolve in the aqueous phase. Next, we did preparation of alpha-beta unsaturated ketone. So in this one, you have to remember about the acidic protons. So in this molecule, we have acidic protons here because this carbon is sandwiched between highly electronegative functional groups. Therefore, this carbon is lacking electrons, so it's more likely to grab electrons from one of these hydrogens. So these hydrogens are acidic hydrogens. Therefore, in the presence of a strong base, one of these hydrogen, like let's say sodium hydroxide, this OH can accept one of these acidic protons and we can obtain the respective carb anion or nucleophile. And we learned that alpha beta unsaturated ketones are when we have a double bond adjacent to a carbonyl group, and the beta carbon is the site of a nucleophilic addition because we had the resonance structures in the lecture slides for this lab, but there's the electron shift towards these carbons due to the oxygen here, and that makes the beta carbon more electrophilic, and therefore that's the site for nucleophilic addition. So this is where we did the Michael addition reaction and aldol condensation. So practice a few of those kind of reactions so you know how to predict the product or predict the reagents if you're given the product. Again, isolation. This time we did a precipitation by cooling the solution. When you cool a solution, the solubility of the compound in that solution decreases, so it precipitates, and we filtered it out and did recrystallization. Okay, I wanted to quickly go over the extraction technique because you could get questions from any point of the extraction process. When we have our final product mixture at the end of these reactions, it was usually our final organic product mixed with maybe excess reagents or byproducts or catalytic compounds. To obtain a pure final product, we need to get rid of these other stuff. So we use extraction as a technique. Usually our final products were very small in volume, and that's why we mix it with some organic solvent in the beginning, like diethyl ether or dichloromethane. I think those two are the two main organic solvents we used for extraction in our class. And the most important reason about them is that they have a very low boiling point, so at the end we can apply gentle heating to get rid of those solvents and isolate our product. So if it so happens our excess reagents or byproducts are something we can convert into an ionic molecule by reacting with the acid or a base, we will wash the organic layer with the respective acid or base to convert those extra reagents into ionic form, so they will move to the aqueous layer. So this is the aqueous organic, so they will move to the aqueous layer and we can remove them by removing the aqueous layer. We usually we wash the organic layer with a saturated sodium chloride solution, and this is a very saturated salt solution, so it has a high capacity to absorb water. Therefore, any water droplets that were trapped in the organic layer should be drawn into the salt layer, and then we can remove the aqueous layer. As a further step, to dry the organic layer, we add anhydrous sodium sulfate, which also has a high capacity to absorb water present in the organic layer. So we do that to make sure the organic layer is completely dry of water. Usually we transfer the organic layer to a fresh vial and apply gentle heating to get rid of that solvent. So we had our final product at the end isolated. If you were asked how would you know which layer is the aqueous and which layer is the organic layer, in the case you do not know the densities of the solvents, you can do a water drop test. That is, add a few drops of water. So the water will definitely mix with the aqueous layer. So you will see one of the two options, right? You could either see the bottom layer grew in size, then that would mean the bottom layer is the aqueous layer. If it was the top layer that grew in size when you added the water drops, that would mean the top layer is the aqueous layer. So even without knowing the densities of the solvents, you can easily identify which layer is organic or aqueous by doing the water drop test. Now, a revision of the recrystallization technique. We do that to get rid of impurities. If we have, usually when we have the crude product, the impurities are trapped within the crude product crystals. We add a recrystallization solvent. This should have a low solubility for the compound of interest at room temperature. So when we warm it, the crystals should have a higher solubility at high temperature. I saw in the lab reports, a lot of students wrote high solubility of the compound at the solvent's boiling point. That doesn't have to be necessary, right? If it's getting soluble at the solvent's boiling point, that means the solvent is boiling off. We don't want that to happen. So it's sufficient to say low solubility at room temperature and high solubility at higher temperatures. And the crystals will dissolve, releasing the impurities. And once we let it slowly cool down back to room temperature, it will form selective crystallizations to obtain the pure crystals, and the impurities are still soluble in the recrystallization solvent. Then by filtration, we can get the pure crystals isolated. So if you're asked what is the definition of a good recrystallization solvent, that would be it has a low solubility of a compound of interest at room temperature, but a higher solubility when the temperature is increased. This is my final slide about calculation of theoretical yield. Let's take a reaction from the Grignard reaction lab, where two phenylmagnesium bromides reacted with one methyl benzoate to give one triphenyl methanol. So the molar ratio is 2 to 1 to 1. This means if you have 2 moles of phenylmagnesium bromide, for that to completely react, we need at least 1 mole of the methyl benzoate. So that is exactly half the amount of the amount you have here. So what if you had 1.5 moles? That is greater than 1 mole. Then methyl benzoate would be the excess reagent, and phenylmagnesium bromide would be the limiting reagent for that example. Because for these 2 moles to react, you only need 1 mole. But if you have 1.5 moles, that's more than you needed, which means this reagent is the limiting reagent. But if the number was, say, lower, then one mole, that means you need at least 1 mole for this 2 moles of phenylmagnesium bromide to completely react, right? But if you don't have that amount, that means methyl benzoate would be the limiting reagent. So in the 2 examples, in the first one, the limiting reagent would be the phenylmagnesium bromide. In the second example, the limiting reagent would be methyl benzoate. So once you decide the limiting reagent, then look at the molar ratio between the limiting reagent and the product. So let's take, since 1-to-1 molar ratio is pretty easy, let's take our second example, where phenylmagnesium bromide was the limiting reagent and the molar ratio between that and the product is 2-to-1. So if you reacted 2 moles, you would get half the amount of product. So theoretically, we could get 1 mole of triphenylmethanol based on this example. And once you know the theoretical number of moles, to get the theoretical yield, you multiply that number by the molecular weight of the product. So I saw in a few lab reports, students forgot to use the molecular weight of the final product and they just used the molecular weight of a reagent, or they forgot to use the amount that was calculated based on the numbers that were weighed for the experiment. So make sure you pay attention to these kind of details, and you should be able to calculate whatever the molar ratio is. Remember, in the ketone reduction experiment, one of these could react with 4 ketones. Because it has 4 hydrogens, right? All 4 of them can attack a ketone at a time, so 4 ketones can be reduced. So the molar ratio for that is 1-to-4. So if you had 4 moles of the ketones, you would need at least a quarter of that from the reducing agent. So 1 mole at least. If the amount you had was less than 1 mole, then sodium borohydride would be the limiting reagent. But if you had more than 1 mole of sodium borohydride, then the ketone would be the limiting reagent. So in that case, if you reduce 4 ketones, you get 4 alcohols So the molar ratio between ketone and alcohol is 4-to-4. It's the same ratio, so it's same as 1-to-1. So whatever amount of ketones you react, you should be able to obtain the same amount for the alcohol theoretically. And then you can apply the same method as here. and get the theoretical yield. So that would be all for the review. Good luck studying, and we will have office hours on Monday. So if you have any questions while you're studying, make sure to come with your questions for the office hours. Thank you.